Section 14 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 10, Solar Energy, Part 2. Solar energy. The Earth depends upon the Sun for its supply of heat and light. The Sun is transmitting heat to the Earth, and unless the supply of energy is being replenished in some way, it is obvious that it must be losing in heat and temperature. From its effect on the Earth, an estimate can be had of the amount of heat radiated by the Sun annually. If it be assumed that the Sun has the same heat capacity as water, and hydrogen is the only substance with a greater heat capacity, it would fall in temperature about 4° Fahrenheit annually. If, therefore, the great luminary were simply a hot body, cooling off, its present rate of radiation could not be maintained for more than 3,000 years. That the Sun has been radiating a much longer period than this is obvious from geological and biological evidence, so that some other cause must be sought. Up to the 19th century, the doctrine of infinite durability was generally held by astronomers and geologists. For that reason, no particular attention was paid to the nature of the heat of the Sun and its source, but with the formulation of the doctrine of the conservation of energy it was realized that the energy of the Earth must proceed from the Sun for the greater part, and consequently it became necessary in turn to question the source of solar heat. Robert Mayer, to whom is due the earliest conception of the conservation of energy, asked himself, "If the Sun is hot, why does it not cool off?" In 1848 Mayer published some answers to his own question in a paper which failed to receive the approval of the French Academy of Sciences. His conclusions were as follows: The Sun cannot be a glowing mass sending out radiation without compensation. Solar heat cannot be due entirely to chemical changes, nor can it be due to solar rotation. In his opinion it was the result of meteors falling into the Sun. He did not overlook the fact that the resulting increase in the mass of the Sun would increase its attraction for the planets and would shorten the sidereal year. This was contrary to the facts of observation, and Mayer was forced to an incorrect conception of the undulatory theory of light to explain the situation. 6 years later, William Thomson, subsequently Lord Kelvin, reached independently almost the same conclusion as Mayer, but he was able to explain the increase in the Sun's mass resulting from meteoric showers, for according to the gravitation theory, the added matter is drawn from space, where it acts on the planets with very nearly the same force as when incorporated in the Sun. Lord Kelvin then ventured an estimate of the age of the Sun, which was the first attempt in this direction made by a physicist. He assumed that the solar energy of rotation was derived from the fallen meteors, which, allowing for the constant loss of solar energy by radiation, could be acquired in 32,000 years. Taking into consideration the limited amount of meteoric matter available near the Sun, he concluded that sunlight cannot last as at present for 300,000 years. This theory attracted little attention when promulgated by him in 1854, and was abandoned by him later. But in the same year Helmholtz, working along the lines of the nebular hypothesis of Kant and Laplace, derived the heat of the Sun from the contraction of the nebula from which the Sun and planets were formed. He asserted also a further contraction of the Sun, now assumed to be in progress, by which the kinetic energy obtained was converted into heat, and compensated for the loss of solar heat by radiation. Accordingly, if the Sun contracts 1/10,000th part of its radius each year, enough heat would be generated to supply radiation for 2,100 years. Helmholtz's computation gives 22,000,000 years as the probable age of the Sun, based on a uniform radiation and homogeneous density of that body. Later, S. P. Langley, with experimental data derived from the direct radiation of the Sun, reduced this age to 18,000,000 years. This theory immediately supplanted that of the falling meteors, which more serious reflection demonstrated could account only for the slight increase in the solar heat as compared with the energy of shrinkage. Lord Kelvin in 1862 returned to the subject, favoring a theory like that of Helmholtz's, concluding that we may accept as the lowest estimate for the Sun's initial heat 10,000,000 times a year's supply at the present rate, but 50,000,000 or 100,000,000 as possible in consequence of the Sun's greater density in his central parts. As for the future, inhabitants of the Earth cannot continue to enjoy the light and heat essential to their life for many million years longer unless sources now unknown to us are prepared in the great storehouse of creation. Studies of the Sun's heat were continued by Lord Kelvin, and in his theory he incorporated a discovery made in 1870 by J. Homer Lane, an American, which paradoxically demonstrated that within certain limits the more heat a gaseous body loses by radiation, the hotter it will become. This theory of Helmholtz's, as modified by Kelvin, encountered a serious rival in 1882, when Sir William Siemens proposed that a rotating Sun hurled by centrifugal action at the equator enormous quantities of gas into space, which returned to it again at the poles, somewhat after the manner of a regenerative furnace. Helmholtz's theory was modified in 1899 by Professor T. J. J. See, who abandoned the German scientist's hypothesis of homogeneous density for the Sun and applied Lane's law, investigating minutely the more complex case of central condensation. As the result of his study, the probable age of the Sun was extended from 22,000,000 to about 32,000,000 years. All of these researches came before the discovery of radium, and when the extraordinary properties of this new substance were known, it was stated that a bare fraction of a per cent of radium present in the Sun would account for and make good the heat that is annually lost by radiation. Should this hypothesis hold good, an entirely new aspect is given to the problem of solar heat and to the heat of the Earth. This innovation, advanced by members of the younger school of physicists, all of whom had prosecuted with vigor researches in radioactivity, did not appeal to Lord Kelvin, who maintained in 1906 that the gravitation theory was still sufficient to account for the Sun's heat. No evidence has been produced of the presence of radium in the Sun, altho helium has been found there. As helium is obtained from radium, the existence of radium in the Sun is quite probable. Sir George H. Darwin, in discussing the effect of these recent discoveries on solar age, says: "Knowing as we now do that an atom of matter is capable of containing an enormous store of energy in itself, I think we have no right to assume that the Sun is incapable of liberating atomic energy to a degree at least comparable with that which it would do if made of radium. Accordingly, I see no reason for doubting the possibility of augmenting the estimate of solar heat, as derived from the theory of gravitation, by some such factor as 10 or 20. It is obvious, therefore, that while the contraction theory explains the origin of a vast amount of the Sun's heat, yet there are other sources of internal energy which recent discoveries plainly indicate are of great importance, so that the scientist at this stage is unable to declare positively the age of the Sun or to make any accurate estimate as to the probable duration of the time through which it will afford light and heat to the Earth and the other planets. Nevertheless, it seems assured that millions of years hence, how many cannot even roughly be determined, the Sun will be reduced from a ball of glowing vapor to a gigantic black cinder rushing through space. Unwarmed by any central luminary, its crust will be washed by oceans of air liquefied by a cold too intense for any living creature to endure. The light of the Sun is obviously more intense than any other luminant known to man. If compared with the full moon, 600,000 times as much light is received from the Sun. Expressed in another way, the Sun gives over 60,000 times as much illumination as a standard candle at a distance of 1 yard. But not all of the light and heat which is radiated from the Sun comes to the Earth. Professor Langley, in his experiment at Mount Whitney in 1881, found that a clear atmosphere would cut off 40% of the rays coming perpendicularly to the Earth's surface. Gases in the atmosphere, such as carbon dioxide, cut off even a greater amount, and the general absorption is greater at the violet end than at the red. It is for this reason that high altitudes and a clear atmosphere are essential for solar investigation, and for this reason, too, that the setting Sun appears red, the bluish rays being absorbed in traversing a greater amount of terrestrial atmosphere than when the Sun is high in the sky. The temperature of the Sun can be estimated from its brilliancy, and from spectroscopic and bolometric studies. It is a common experience that a filament of an incandescent lamp emits more light and glows more brightly when the amount of current is increased. At first the filament is red, but as more current is permitted to flow it becomes yellow, and finally a brilliant white. This is marked by an increase in temperature, and secondly, the temperature depends upon the brilliancy of the glow. The same analogy holds good in the case of the Sun and the stars. If the wave length of the radiation is known, and the color which emits the greatest amount of heat in the spectrum, and this can be measured by the bolometer by a simple law, it is possible to calculate the absolute temperature of a star. Then, by deducting 270 degrees from the result, its temperature in the ordinary centigrade degrees is obtained. Thus, in the case of the Sun, the maximum heat radiation occurs in the greenish yellow light, which gives a temperature for the rotating disk of the Sun of about 5,000 degrees centigrade or 9,000 degrees Fahrenheit. The atmospheric absorption already referred to serves to cut down the intensity of the radiation, so that, taking this and other amounts into consideration, the temperature of the Sun's disk can be estimated at about 6,200 degrees centigrade. Similar investigation in the case of Sirius and Vega, which are white or younger stars, give a temperature about 1,000 degrees Celsius higher than that of the Sun, while the red star Betelgeuse, which is a declining star, older than the Sun, has a temperature some 2,500 degrees centigrade less. The temperature of the Sun furnishes different results, depending on the manner in which the problem is attacked. Arrhenius, in his work on "Worlds in the Making," summarizes recent work and states that from the intensity of the radiation, Christiansen and afterward Warburg calculated a temperature of about 6,000 degrees centigrade. Wilson and Gray found for the center of the Sun 6,200 degrees, which they afterward corrected into 8,000 degrees. Owing to the absorption of light by the terrestrial and the solar atmospheres, two low values are always found. That applies to a still greater extent to any estimate based upon the determination of that wavelength for which the heat emission from the solar spectrum is maximum. Le Chatelier compared the intensity of sunlight filtered through red glass with the intensities of light from several terrestrial sources of fairly well known temperatures treated in the same way. These estimates yielded to him a solar temperature of 7,600 degrees centigrade. Most scientists accept an absolute temperature of 6,500 degrees, corresponding with about 6,200 degrees centigrade. That is what is known as the effective temperature of the Sun. If the solar rays were not partially absorbed, this temperature would correspond with that of the clouds of the photosphere. Since red light is little absorbed, comparatively, Le Chatelier's value of 7,600 degrees centigrade and the almost equal value of Wilson and Gray of 8,000 degrees centigrade should represent approximately the average temperature of the outer portions of the clouds of the photosphere. The higher temperature of the faculae is evident from their greater light intensity, which, however, may be partly due to their greater height. Carrington and Hodgson saw, on September 1, 1859, two faculae break out from the edge of a sun spot. Their splendor was 5 or 6 times greater than that of the surrounding parts of the photosphere. That would correspond with a temperature of about 10,000 or 12,000 degrees centigrade. The deeper parts of the Sun which broke out on these occasions evidently have a higher temperature, and this is not unnatural, since the Sun is losing heat by radiation from its outer portions. At all events, the Earth receives a large amount of energy in the form of light and heat, which amounts to 3 horsepower for every square yard of space perpendicular to the Sun's rays. And while this really is not readily available for mechanical purposes, yet solar engines have been constructed in which this energy has been transformed into power. While the energy of the Sun is not, generally speaking, available for mechanical purposes, yet indirectly the heat received by the Earth has made possible plant and animal life, on which depends the source of all energy. The transmission of the Sun's heat to the Earth is one of the important problems of present-day physics and meteorology, inasmuch as the amount of radiation or heat emitted by the Sun, spoken of by physics as the solar constant, and the relation of this radiation to terrestrial temperature, as well as the study of the radiation of different parts of the Sun's disks, are all topics of fundamental importance. The solar constant is measured outside of the Earth's atmosphere at mean solar distance, and the intensity of radiation is employed for a unit, which, when fully absorbed for 1 minute over a square centimeter of area placed at right angles to the ray, would produce sufficient heat to raise the temperature of a gram of water 1° centigrade. If once the original quantity and kind of heat emitted by the Sun be known, its effect on the constituents of the atmosphere on its journey to the Earth, how much of it reaches the soil, how through the change of the atmosphere it maintains the surface temperature of our globe, and finally how, in diminished quantity, or altered kind, it is returned to outer space, it would be possible to predict nearly all of the phenomena of the weather. Thus it has been known that when there is a small decrease in the solar radiation, there follows a marked and general decline in temperature. So that, knowing the variation of radiation, it should be possible to predict changes in climate. These data are secured by measuring the total intensity of the radiation, as it arrives at the Earth's surface, with the pyrheliometer, or thermometer with blackened bulb, carefully protected from all other influences except the direct rays of the Sun; and in the second place by measuring the heat or energy in different parts of the solar spectrum with the spectrobolometer. The absorption of the atmosphere nearer the Earth for different areas requires measurements to be made at several stations; for at Washington, near the sea level, the intensity of radiation actually observed is only about 3/4 as great as that observed in the clear atmosphere of Mount Wilson at a height of 6,000 feet. Recent observations made at Mount Wilson and Washington by Mr. Abbot, of the Astrophysical Laboratory of the Smithsonian Institution, indicate that heat sent out to the Earth from the Sun in the course of a year is capable of melting an ice shell 114 feet thick over the whole surface of the Earth. The solar radiation is not a constant quantity, but varies with the decrease in solar distance, the changes occurring from month to month and from year to year. The variation is due to the changes in the source of radiation rather than to the effects of our atmosphere or external causes. The distance and position of the Sun as regards the other members of the solar system has been considered in a previous chapter. It is known that its apparent diameter is 32 arc minutes 4 arc seconds, which corresponds with 866,500 miles, or 109½ times the diameter of the Earth. This would give it an area 11,950 times that of the Earth and a volume 1,306,500 times greater. The actual mass of the Sun is 332,000 times that of the Earth, but its average density is only about a quarter as great, so that the Sun, which has a density of 1.41 as compared with water, is 4 times as large as it would have to be if its density were the same as that of the Earth. Taking into consideration this lightness as well as the high temperatures prevailing in the Sun, one is forced to the conclusion that the body of the Sun must be in a gaseous state. The conditions under which the gases are found must be quite different from those with which we are acquainted on the Earth. Gravity at the surface of the Sun exceeds by more than 27 times gravity on the Earth. The motion of the Sun as regards the other stars in the heavens has been treated elsewhere, but it is proper here to refer to its rotation on its axis from west to east, which takes place in a period of about 25 days and is apparent from the motion of the sun spots, though it can also be detected by directing a spectroscope toward the edges of the limb and noting by Doppler's principle how one side is approaching the observer and the other is retreating. The time of rotation is not the same for all parts of the disk, but depends upon the position of the spots selected. Those nearest the equator show the most rapid rotation. End of section 14.